And this is the last video. It's for 4 complex numbers. So again, you have some examples up there. So we're going to start with square root of negative 72. So since it's the square root of a negative, we know it's going to be an imaginary number. So what you want to do is break it up into the product of -1 and some real numbers. But since it's under the square root, we want to reduce it. So we want it to be numbers, at least one of them, a number that is a perfect square so that it will reduce. And if there aren't any, then we just can't reduce it that much. But for 72, 36 is a perfect square that divides evenly into 72. So I'm going to break up 72 into -1 times 36 times 2. It's still negative 72. And now that property where you're multiplying under the square root, you can break it up into the square root of each piece as long as at least one of them is positive. And if you have two negatives, you have to be careful. So square root of 36, square root of 2, so we can do this. Square root of -1 is I, square root of 36 is 6, and square root of 2 has to stay square root of 2 because it doesn't reduce. And then in the correct order, 6i square root of 2. So answer for number 1. Number 2, we've got some variables thrown in there. We didn't do variables in class, but they work the same way as a number would. So I'm going to break this up into -1 again, because I know it's going to be imaginary, times, let's break up the 24 into a perfect square and another number. So that's 4 and 6. And then x to the third. What perfect square is a factor of x to the third? X squared, so it's x squared times x instead of x to the third. Same thing though. And then y to the fifth, actually y to the fourth is a perfect square because the square root of y to the fourth is just y to the second. So it's y to the fourth times y. We're going to write that instead of y to the fifth, just like we wrote 4 times 6 instead of 24. And we're still taking the square root of all of that. And now we can take the square root of each piece and multiply them together. So this is all multiplication. So the square root of -1 is I. Square root of 4 is 2. Square root of 6, we don't know, so leave it. Square root of x squared is x. Square root of x, we don't know, leave it. Square root of y to the fourth is y squared. Oops. And the square root of y we can't reduce. Now we can simplify this because I've got numbers that are not under the square root that I can multiply together. Real number goes first, then imaginary part. So we're going to do I times 2 times x times y squared, which is 2i x y squared. All that multiplied together, times the square root pieces. Since they're all underneath the square root, we can put them back underneath the same square root. So it's times the square root of 6xy. So 2i x y squared times the square root of 6xy. Then we have I to the 65th we need to reduce. We know that I squared is equal to -1, so we want to break it up into I squareds. First we want to make it into an even number, and I. So it'll be I to the 64th times I. So we took care of the fact that this number is not even, so we can't just divide by 2. So we want to break it up into a number that is divisible by 2 and 1. So this is really I to the first here. Then I to the 64th, we're going to figure out how many I squareds are in that. So I squared to what power would give me 64? And that's to the 32nd power. Still times I. Then, I'm going to move up here, I squared is equal to -1. Still need to take that, though, to the 32nd power, times I. If you take a negative number 32 times, an even number of times, it becomes positive. So it's -1 to the 32nd power is +1 times I, which gives us a final answer of I. Number 4. We're going to break this up into square root of -1 times 81, because 81 is a perfect square, 9 times 9. And x to the 6 actually is a perfect square. would be x to the third times x to the third, because you add exponents when you're multiplying. So then we're just going to take the square root of each piece. So square root of negative 1 is I, square root of 81 is 9, and the square root of x to the 6th is x to the third. In the correct order, final answer 9i x to the third. Number 4, we're multiplying, so we have to FOIL. 2 times 2 is 4. 2 times negative I is negative 2i. I times 2 is positive 2i. And then I times negative I is negative I squared. So we need to simplify, so 4, and then these two cancel out. And then minus I squared, but I squared is negative 1. So minus a negative 1, which makes it 4 plus 1, which makes our final answer 5. So notice complex times complex gave us real because these two are complex conjugates. Number 5, just like you would multiply like 2 times 4 times 5, you take 2, multiply them, and then multiply that result by the last one. You don't distribute because there's not two terms here. They're all part of the same term. So for this one, let's just pick the first 2 to multiply. And actually, for this one, we can do it in any order we want, so we can just rearrange the numbers too. So I'm just going to put all the numbers together, and then I times I is I to the third. So this would be negative 6, and still times 5i to the third, which is negative 30i to the third. But you can't leave I to any power besides 1. So I'm going to break that up into I squared times I. That's still I to the third, but I know that I squared is negative 1. So negative 1 times I, still times negative 30. And then I can simplify that. So negative 30 times negative 1 is positive 30, so your final answer is 30i. Number 6. Oops, I just noticed I had 2 number 5s on here. So the second number 5, we're going to solve this. I'm going to go over here to solve. So since this quadratic does not have a linear term, there's no bx term, we can solve by taking square roots. And this one we'll have to because it's not factorable otherwise. We could pull out a 5, but it would still need to be solved by taking square roots. So I'm just going to subtract 45 from both sides to get 5x squared equals negative 45. Divide each side by 5 because you want to do that before you square root, otherwise you're going to mess it up. Equals negative 9. Now you're going to square root both sides. Because you took the square root, it has to be plus or minus over here. This is a variable, so it would definitely be whatever x is. Over here it has to be plus or minus square root of negative 9. But the square root of negative 9 is the square root of negative 1 times the square root of 9, which is I times 3, which is 3i. So x equals plus or minus 3i. Final answer in solution sets. And you can actually check your answers for these ones too. If you plug this back in, plus or minus 3i here, you will get the correct answer. It will equal 0. Number 6, 4x squared plus 24. Again, we're going to solve by taking square roots because there's no linear term. So it's 4x squared equals negative 24. Now, you can take the square root right now. You just have to be careful. Because if you square root both sides, you still have a plus or minus square root of negative 24, which needs to be reduced. But on the right side, on the left side, you have 2x. So you square root both of those pieces. But if that number was something like 5, like on the last one, you go back to the last one. If you tried to do that here, here's what you would get, square root. You get square root of 5 times x equals this plus or minus square root of negative 45, which would then need to be reduced, which we didn't have to do over here because we divided first. And then a lot of people forget that it's the square root of 5, and they might just put 5x, which would be wrong because that would mean this was 25x squared. So that's why I suggest always dividing first. And then, so back down here, we're not going to, I'll do it this other way too, because sometimes it can work nicely. But in general, I divide first. So over here, we're going to divide by 4 to get x squared equals negative 6. Now we take the square root. You took the square root, it's got to be plus or minus, so it's x equals plus or minus square root of negative 6. We got to reduce that. No perfect square goes into 6. Okay, so we just got it, but we still have to take the I out. So it's the square root of 1, negative 1 times square root of 6. But the square root of negative 1 is I. So it's just plus or minus I square root of 6. So if it doesn't reduce, you still have to leave it under the square root and get the negative out. So final answer in solution sets plus or minus I square root of 6. If you were to finish it this other way, over here, you would have to break this up into square root of negative 1, square root of 4, square root of 6, because that's 24. I'm just going to skip some steps here. This would be 2, this would be I, so it's 2I square root of 6 equals 2x. Then you'd still have to divide by 2, which this reduces to 1, so it would be x equals plus or minus I square root of 6. So you get the same answer. That way it's just sometimes more complicated to do. Number 7, negative 9x squared equals 9. It's already set up nicely for us, so we're just going to divide by negative 9. To get x squared equals negative 1, you're familiar with this solution. Square root both sides to get x equals plus or minus, because we took the square root of negative 1, which is just I, so it's x equals plus or minus I. And final answer in solution sets. Last one on this page, 7x squared plus 84. So we're going to solve by taking square root since there's no linear term. So 7x squared equals negative 84. 5 by 7. X squared equals negative 12. Now we square root. So since we took the square root, it's plus or minus the square root of negative 12, which will be broken up to square root of negative 1, square root of 4, square root of 3, that product, plus or minus. And so it's plus or minus square root of negative 1 is I, square root of 4 is 2, square root of 3 stays, square root of 3. And in the correct order, 2I square root of 3. So final answer in solution sets is plus or minus 2I squared of 3. Okay, the next page is adding, subtracting, and multiplying, dividing rational complex numbers. So make sure you know what your operation is. Okay, for number 1, we are adding. So since we're adding, we can just drop the parentheses and combine like terms. Real plus real, imaginary plus imaginary. So negative 4 plus 6 is positive 2. And then 2I minus 3I is negative I. And remember, has to be in the form A plus BI. So in this case, A is 2 and B is negative 1. Number 2, we are subtracting. So you need to distribute the negative. And then you can drop parentheses. So it's minus 3 and then minus a negative 2I, so it's plus 2I. Since I distributed the negative, I can drop parentheses. Now combine like terms. 5 plus a negative 3 is positive 2. And then negative I plus 2I is a positive I. So it's just 2 plus I. A is 2 and B is 1. Number 3, you're adding again. So again, we don't need the parentheses. Combine like terms. 6 plus 4 is 10. Negative 3I minus 2I is negative 5I. So A is 10, B is negative 5. Number 4, we're subtracting again, so we need to distribute the negative. So it's actually subtracting 1 and then subtracting a negative 5I, which is adding 5I. Since I distributed the negative, I can drop parentheses. Combine like terms. Negative 11 minus 1 is negative 12. 4i, plus 5i is plus 9i. So A is negative 12 and B is 9. Number 5, we are adding, so no parentheses needed, so just add the right terms. And so it's going to be 16 plus 0, which is just 16. Number 6, distribute the negative because we're subtracting. It's really adding 6 and adding 3i. Since I distributed the negative, I can drop parentheses. Add real to real, so that's 11. Imaginary, imaginary, plus 5i. So A is 11, B is 5. Here we're multiplying because they're side by side. There's no sign in the middle, so it's multiplying. So we got a FOIL. So 2 times 3 is 6. 2 times negative I is negative 2i. I times 3 is positive 3i. And I times negative I is negative I squared. We know what I squared is, so we have to reduce that and combine like terms. So I'm going to leave my 6, and then negative 2i times plus 3i is positive 1i, and minus I squared, which is negative 1. So this becomes 6 plus I plus 1, so 7 plus I. So A is 7 and B is 1. Number 8, we are also multiplying, so 5 times 4 is 20. 5 times I is negative 5i. Negative 2i times 4 is negative 8i. And negative I times negative 2i is positive 2i squared. Again, we're going to have to change I squared to negative 1 and add these like terms. So we'll get 20 minus 13i plus 2 times negative 1, because that's I squared. So I'm going to go up here, will be 20 minus 13i, and then minus 2, this is 2 times negative 1, and then combine like terms. 20 minus 2 is 18, so it's not negative 18 though. Positive 18 minus 13i, so A is 18 and B is negative 13, and it has to be in that order. All of these have to be in the order that I put them in. Number 9 is multiplying again. So we need to distribute. 4 times 1 is 4. 4 times negative 2i is negative 8i. Negative 2 times 1 is negative 2i. It was negative 2i times 1. And then negative 2i times negative 2i is positive 4i squared. Combine like terms, so 4, negative 8i minus 2i is negative 10i. And then we have to change this to I squared. So it's plus 4. I'm sorry, we have to change the I squared to negative 1. It's 4 times negative 1. So this is 4 minus 10i. And then it's going to be minus 4 because it's 4 times negative 1. Combine like terms, that zeroes out. So your final answer is negative 10i. It's just an imaginary piece. So A is 0 and B is negative 10. Now the fun ones. So we're not actually dividing, we're just rewriting, because you can't leave an imaginary number in the denominator. So to make the denominator a real number, we have to multiply by the complex conjugate. So that's like a difference of squares pattern to make the linear term go away or the imaginary term go away. So it's just the same binomial as the denominator, just the opposite sign. So this will cause a difference of squares pattern to occur, which will get rid of the imaginary term and make an I squared term, which is a real number. So we have to distribute, so we're going to put it in parentheses to help us remember that. So 5 times 3 is 15. 5 times negative I is negative 5i. Over 3 times 3 is 9. 3 times negative I is negative 3i. And look, nice things happen. Then we're going to add 3i, which is I times 3, and then I times negative I is negative I squared. So this becomes still 15 minus 5i in the numerator. In the denominator, 9. This is zeroed out. Minus I squared, which is negative 1. So minus a negative 1. So now that gives us, I'm just going to keep going down, 15 minus 5i over 9 plus 1. So 15 minus 5i over 10. But our final answer has to be in the form a plus bi, so we have to split it into two fractions. And even if we didn't, if we left it as a fraction, we would still have to reduce because each of these numbers is divisible by 5. Let's just split it up into two fractions though. So it's going to be 15 over 10 minus 5 over 10i. You want to make sure the i is on the outside, because having it on the outside is the same thing as having this like over 1, so it'd be 5i over 10, but we want the i on the outside. Then we can reduce, so we'll come down here to reduce. Each is divisible by 5, so it'd be 3 over 2 minus 5 goes into 5 once, into 10 twice, so 1/2. So 3/2 minus 1/2 I. So in this case, A is 3/2 and B is negative 1/2. So what I was talking about, if you just reduce this guy right here, would be divide everything by 5 would be 3 minus I over 2. But again, we need to have it in A plus BI form when we're just doing these solving, just multiplying, not solving a problem. So we need to split it up into two fractions. Number 11 looks tricky, but it's actually the easier one. It's okay, since it's not a binomial, it's not as hard to get rid of the imaginary part. And since there's a 2 down there, but that 2 is not bothering us, so we don't have to worry about the 2. So all we need to do is multiply by I over I. Because if we do that in the denominator, it'll make an I squared, which is a real number. 2 is just fine there. So don't do more work than we have to. Do put this in parentheses though, so remember to distribute the I to both of them. So I times 7 is 7i. I times negative 13i is negative 13i squared over 2i times I, which is 2i squared. So this becomes 7i minus 13 times negative 1, because that's I squared, over 2 times negative 1. Again, that's I squared. I'm going to bring it down here. So 7i plus 13 over negative 2. Put it in the right order. 13 plus 7i over 2, negative 2. Split it into two fractions. So it's going to be negative 13 over 2, because we want to keep the negative in the numerator. And then instead of doing plus 7i over negative 2, just subtract it, because this fraction would be negative anyway. So just subtract a positive 7 over 2i. And that's your final answer. So A is negative 13/2, B is negative 7/2. And the last one is just like the number 11. All we need to do is get rid of the I, so we're just going to multiply by I over I. We don't need to worry about the 3. Distribute through the top, so it'll be 6i minus 5i squared over 3i squared. So in the numerator, it becomes 6i minus 5 times negative 1, because negative 1 is I squared, over 3 times I squared. Oh, just kidding. I meant to change that to negative 1. So I squared is negative 1. So that becomes 6i plus 5 over negative 3, which is in the right order, 5 plus 6i over 3. And again, we need to split it into two fractions to get it in the proper form. 5/3 plus 6/3 I, which is actually 2. So it's 5/3 plus 2i. So A is 5/3 and B is 2. Darn it, I forgot to put a negative here. So it should be negative 3, so we're subtracting this actually. So we're going to have 5 minus negative 5/3 minus 2i. That's your final answer. So A is negative 5/3 and B is negative 2. Last page is equating imaginary or complex numbers. So we're trying to solve this equation. So we know since this has a real and imaginary part, this has a real and an imaginary part. This is supposed to be a lowercase I, by the way. Since they both have a real and imaginary part, they don't affect each other. So we know that the real part has to equal the real part, and the imaginary part has to equal the imaginary part. So we set up two equations. So we're going to have 15, real part on the left equals real part on the right. Solve for L. So L will equal 5 to make this true. And then we do for the imaginary part, that negative 28. We don't have to worry about the i's, so don't worry about that, but you do have to worry about the sign here, because that's actually the b value. B equals b. The b in this one is equal to the b in this one. So negative 28 equals 4m. Solve for m. Negative 7 is equal to m. And then you can check your answer by plugging it back in. If we plug in 3 times 5 is 15, so the real equals real. Negative 7 times 4 does give you negative 28. So it is correct. For number 2, we're going to do the same thing. So real equals real. So we got 6 minus L equals negative 12. So I'm going to subtract 6 from both sides to get negative L equals negative 18. So we just divide by negative 1, so L equals a positive 18. And then for my second one, we have imaginary equals imaginary. So 3m equals 27, divided by 3, and m equals 9. So m has to equal 9, and L has to equal 18 for this to work. And again, we can check 6 minus L. 6 minus 18 is negative 12. Good. 3 times 9 is 27. Next one, imagine a real part equals real part. So we have 3L plus 4 has to equal 16. Because remember, they don't affect each other. That's why we can do this. Subtract 4 be 12. 3L equals 12. Divide by 3. And that gives us L equal to 4. And then we have imaginary part equals imaginary part. 3 minus m equals negative 3. Don't forget that sign. Subtract 3 from both sides, you get negative m equals negative 6. Divide by negative 1, which gives us m equal to a positive 6. Again, we can check this. If we have positive 4 for L, that would make this 12 plus 4 is 16. And then we have for Y, m was 6. So 3 minus 6 is negative 3. So we're good. Last one of this kind. Real equals real, so 7 plus m equals 3. Just going to go ahead and solve this one. So m equals negative 4. And then imaginary equals imaginary. So 4L minus 10 is equal to negative 6. Add 10 to both sides, you get 4 equals 4L. Divide by 4. So L equals 1. So we can check if m is negative 4, this would be positive 3, which it is. And if L was 1, 4 times 1 is 4 minus 10 is negative 6. So we're good. All right, last two. Impedance. We have 1 plus 3j ohms. Remember that j is the same thing for I in engineering for these problems. So j squared would be negative 1. And then impedance in another part is 7 minus 5j. Add these complex numbers. So you're just going to do 1 plus 3j plus 7 minus 5j. So just, since we're adding, you can drop the parentheses, add like terms. So it's going to be 8 minus 2j. And the very last one, we have this formula E equals IZ, where I is 3 minus j amps. So I'm going to do this here. I equals 3 minus j. So it's E equals IZ, where I is impedance and I is not impedance, it's current. So E is the voltage, I is the amps, current in amps, and Z is impedance. So we are told that Z, the impedance, is 3 plus 2j, and we're trying to find the voltage, which is E. So to find voltage E, I take impedance Z times the current I. So to find E, I just have to take I, which is 3 minus j, times Z, which is 3 plus 2j. So since I'm multiplying, I got to distribute. So 3 times 3 is 9. 3 times 2j is 6j. Negative j times 3 is negative 3j. And negative j times 2j is negative 2j squared. And again, they use j instead of I, so we're really just talking about I here. Combine like terms would be 9 plus 3j, and then we have to change j squared to negative 1, because it's just I. So it's 9 plus 3j, and then negative 2 times negative 1 is adding 2, and then you combine like terms here, so it'd be 11 plus 3j. That is your voltage. And that is the last problem for the quiz review.